When you're driving, it's one of those things you just do, right? Press the brake pedal,
Absolutely, second nature.
and boom, this, multi-ton machine starts slowing down nice and smooth. It kind of feels like magic sometimes.
It really does.
But have you ever really stopped to think about the incredible engineering happening just under your foot? That simple push?
It unleashes this whole cascade of forces. It's quite something, all designed for one critical thing: stopping safely,
Yeah.
every time.
Tons of moving metal reliably.
Exactly. And it's this profoundly complex system, all hidden away, working constantly. We barely give it a thought.
Well, today we're definitely giving it a thought. We're pulling back the curtain.
Yep.
Taking a deep dive into the honestly fascinating world of automotive brakes. We're going to unpack these systems piece by piece,
From the basic physics, the hydraulics.
all the way to the super high-tech electronic stuff in modern cars.
Right. And the goal here, our mission for you, is to give you this shortcut, a way to get really well informed about one of your car's most vital systems.
It's not just how they work, is it? It's about understanding what it takes to be an expert.
Precisely. The kind of deep knowledge that gets technicians ASE certified.
Ah, yes, that mark of excellence you hear about.
It really is. It signifies real competence in the industry.
Okay, so our insights today are coming mainly from a pretty comprehensive self-study guide for the ASE Certification Series A5 brakes test.
That's the core source, plus some other materials looking at the diagnostic tools and solutions the pros use.
So get ready. There might be some surprising facts, maybe a few aha moments. You'll definitely leave with a new appreciation next time you hit that pedal. Let's jump in.
Let's do it.
Okay, so ASE certified, we hear that term thrown around a lot. It's like shorthand for this mechanic knows their stuff.
It really is.
But what exactly is ASE? What does it stand for?
So ASE is the National Institute for Automotive Service Excellence. It's actually a nonprofit organization.
Oh, okay. Nonprofit.
Yeah, founded way back in 1972. And their core mission is pretty simple, but super important: improve the quality of car service and repair.
How do they do that? Through testing.
Exactly. Through voluntary testing and certification of technicians. Think of it like an independent check, a rigorous validation of their knowledge and skills.
So it's not mandatory, but it shows competence.
Precisely. It's all about ensuring competence, promoting professionalism, and honestly, giving you, the consumer, a reliable way to spot qualified techs in a field that's getting, well, incredibly complex.
No kidding. Cars are like computers on wheels now.
Pretty much.
So it sounds like a big deal. How many technicians actually go through this? Is it widespread?
Oh, it's huge. Hugely widespread, which really speaks to how valuable it is. Right now, there are over 400,000 professionals holding at least one ASE certification.
400,000. Wow.
And get this, roughly 75%, three-quarters of all working technicians are certified in at least one area.
That's impressive.
It is. And some technicians go even further. They pass multiple tests across different vehicle systems and earn master technician status.
So it's like levels of expertise.
Exactly. And it works both ways. For you, the car owner, it's a signal, right? Helps you find someone with proven skills. For technicians, it's proof of their knowledge. It often leads to better pay, more trust, career advancement.
Makes sense.
And it really highlights that commitment to, constantly learning in a field where the tech changes, like, every year.
So for our deep dive today, we're zeroing in on one specific certification, the A5 brakes.
That's the one.
And this isn't just a small part of a bigger test, right? It's all about brakes.
100%. The A5 test is entirely focused on brake systems. It's incredibly comprehensive.
Okay, so what areas does it actually cover? What does a tech need to know to pass this?
It breaks down into 4 main content areas, and they're weighted based on, how often these tasks come up in the real world. The biggest chunk, about 43% of the question.
Nearly half the test.
Yeah, almost half. That's on hydraulic, power assist, and parking brake systems diagnosis and repair. This is the core stuff. Master cylinders, all the different valves controlling pressure, how to properly bleed the system.
Get the air out.
Exactly. Crucial. Then the power assist units, vacuum boosters, hydro boost, and even the parking brake systems. Mastering this is fundamental.
Okay, what's next?
Next up, about 11%, maybe 5 questions or so, covers drum brake diagnosis and repair.
Still relevant then, even with discs everywhere.
Oh, absolutely. Still common on rear axles. And you need to understand their unique quirks, how they fail, how to fix them.
Got it. What else?
Then a pretty significant section, about 24%, focuses on disc brake diagnosis and repair. This is everything about discs, rotors, calipers, diagnosing pulsations, noise, proper pad replacement. Standard stuff on most fronts, now often rears too.
Makes sense. That leaves about...
About 22%, roughly 10 questions dedicated to the really high-tech area. The electronic brake control systems, diagnosis and repair.
Okay, this is the ABS, traction control, that kind of thing.
Exactly. Anti-lock brakes, ABS, traction control, PCS, and electronic stability control, ESC. Understanding how these computer systems integrate with the hydraulics, how to diagnose sensor issues or module problems. That's critical for modern vehicles.
Wow, yeah. It's clearly structured around real-world stuff. So the study guide, it prepares you for multiple-choice questions based on actual tasks a tech would do.
That's the whole idea. It's not just memorizing facts. It's about applying knowledge. And understanding the types of questions ASE asks actually helps you think like a technician.
How so? Are there different formats?
Oh, yeah. 5 main types. First, you've got your direct or completion questions. Pretty straightforward.
Great.
Here's the situation. Pick the single best answer.
Like, what's the most likely cause of X?
Sort of, but even more direct sometimes. Like, if you hear air from the tailpipe during a leak test, what's likely failed? Simple cause and effect.
Okay.
Second, there are most likely questions. These test your diagnostic thinking. Given a set of symptoms, what's the most probable cause or the most correct repair path, forces you to prioritize possibilities.
Right, because there could be multiple possible causes, but one is more likely.
Exactly. Then the third type, and this one really tests critical thinking, is the Technician A and Technician B format.
Ah, I think I've seen those. 2 texts, 2 opinions.
Precisely. You get 2 statements. Tech A says this, Tech B says that. You have to figure out is A is right, B is right, both, or neither. It really mirrors real shop scenarios where different people might approach a problem differently.
Or one might be completely wrong.
Happens all the time. It forces you to analyze both statements critically.
Okay, what else?
Fourth is the accept question. These flip it around, they list several options, and you have to identify the one that is not true or not applicable.
So all of these cause brake squeal acceptee.
Perfect example. You need to know what doesn't fit the pattern. It requires a really solid understanding.
Tricky. And the last one.
Least likely questions. Similar to accept, but asks for the least probable cause of a specific problem. Again, forces you to weigh probabilities and rule out the unlikely culprits. Really hones that diagnostic intuition.
It sounds like they're really testing problem-solving skills, not just recall.
Absolutely. And the test itself is computer-based now, usually about 30 minutes for these A-series tests. You can flag questions you're unsure about, come back later, review everything before you submit. It encourages that methodical approach techs need.
Okay, let's get into the brakes themselves. The core principle.
Yeah.
You mentioned hydraulics. That's where it gets kind of mind-bending, how your foot stops a huge car.
Right. It all comes down to a fundamental principle of physics, Pascal's law.
Named after Blaise Pascal.
The very same. 17th century scientist, mathematician, inventor, brilliant guy. His law is elegant, really. It says that pressure applied to a confined, incompressible fluid.
Like brake fluid.
Exactly.
All right.
That pressure is transmitted equally in all directions throughout the fluid without diminishing.
Okay, so the pressure spreads out evenly.
Yes, but here's the kicker, the aha moment. How it creates this massive mechanical advantage. Your foot pushes a small piston in the master cylinder. That generates pressure.
Right, force over area.
Correct. Now, because that fluid is incompressible, that same pressure gets transmitted to much larger pistons at the wheels and the calipers, or wheel cylinder.
Larger piston, so same pressure, bigger area means more force.
Bingo. That's the multiplication. Your relatively small foot force gets magnified enormously at the wheels. Without Pascal's law, you'd need superhuman leg strength just to slow down. Driving would be totally different, maybe impossible for most people.
Can you give us like a simple numbers example just to visualize it?
Sure, let's simplify. Imagine you push with just 1 pound of force on a master cylinder piston that has a surface area of, say, half a square inch, 0.27 square inch.
Okay, 1 pound on half a square inch.
The pressure is force divided by area, so 1 divided by 0.5, that's 2 pounds per square inch, or 2 psi, pretty low pressure.
Right.
Now, that 2 psi travels through the fluid to a wheel cylinder piston. Let's say that piston is bigger, maybe 1.25 square inches.
Okay.
The force generated there is pressure times area. 2 psi times 1.25 square inches. That's 2.5 pounds of force.
Ah, so 1 pound of foot force became 2.5 pounds at the wheel.
Exactly. You've multiplied the force. Now scale that up. Real master cylinders generate hundreds, even thousands of psi, and the wheel pistons are much larger. You end up with thousands of pounds of clamping force at the wheels.
That's incredible. Pure leverage through fluid.
Engineered leverage, yeah. It's brilliant.
So The master cylinder, that's
Yeah.
the starting point. The brain of the operation converting my foot push into that pressure.
Absolutely. The brain, it takes your mechanical push on the pedal and transforms it into hydraulic pressure. Inside, it's got these primary and secondary pistons, springs, the reservoir on top you check.
Right, where you add fluid.
Yep. And a really key feature of almost all modern ones is the dual hydraulic system.
Dual system,
Yeah,
meaning two separate circuits.
exactly. Two completely separate hydraulic circuits within the same master cylinder body. Usually one circuit handles the front brakes, the other handles the rear. Or sometimes it's a diagonal split, left front, right rear on one, right front, left rear on the other.
Why split it? Is that for safety?
100% safety. Imagine you get a leak. A brake line rusts through or gets damaged. Catastrophic failure in one circuit.
You lose all your brakes.
Not with a dual system. If one circuit fails, the other one is completely independent and can still provide braking, usually to at least two wheels.
Ah, okay. So you can still stop even if it feels different.
Exactly. Your pedal might go lower, you might need more effort, but you can still stop. It's a critical, life-saving redundancy.
And inside that master cylinder, there are smaller parts doing specific jobs. I've heard terms like compensating port, residual pressure valve.
Yeah, tiny but crucial bits managing the fluid flow and pressure. The compensating port is a small opening near the rest position of the piston. When you release the brake pedal, this port opens and allows any excess fluid pressure to bleed back into the reservoir.
Why is that important?
It prevents pedal drag. If pressure didn't fully release, the pads or shoes would stay slightly applied, causing wear, heat, bad fuel economy. This port ensures a complete release. It also lets fluid expand back when it gets hot.
Makes sense. And the residual pressure valve.
Okay, this one's usually only found in the circuit going to drum brakes. It's a small valve that maintains a very slight constant pressure, maybe 5 to 20 psi, in the drum brake lines, even when the pedal is released.
Why keep pressure on drum brakes?
It keeps the rubber cups inside the wheel cylinders slightly expanded against the pistons. This helps prevent air from being sucked into the system past the seals, especially on older systems, and it keeps the shoes closer to the drum for a quicker response, less pedal travel needed.
But you said drum brakes, not discs.
Correct. You absolutely do not want residual pressure in a disc brake circuit. Disc pads need to retract fully and immediately from the rotor to avoid constant drag, noise, and overheating. So no residual valve for discs.
Got it. So the fluid flow, pedal down, primary piston moves, builds pressure, pushes secondary piston, builds pressure in the second circuit.
You got it. Then pedal up, springs return the pistons, compensating ports open, fluid returns to reservoir, ready for the next stop. It's a constant cycle.
Okay, let's talk about the fluid itself. We just top it up, right? But it seems way more critical than just being, well, fluid.
Oh, it's absolutely critical. The
Yeah.
lifeblood, really. And yeah, there are different types. Most common are DOT3, DOT4, and DOT 5.1. These are all glycol-based. Then there's DOT5, which is silicone-based. Totally different stuff.
DOT numbers, what's the key difference?
The single most important spec is the boiling point. Brakes get hot, right? Friction creates immense heat.
Definitely, especially going downhill.
Exactly. If that heat makes the brake fluid boil, it turns into a vapor, a gas. And unlike liquid, gas is compressible.
So you press the pedal.
And you're just squishing gas bubbles instead of pushing solid fluid. Your pedal feels spongy, goes to the floor.
Yeah.
You lose braking power, catastrophic failure.
Very. So higher boiling point is better.
Absolutely. Fresh DOT3 boils around 401 degrees America. DOT4 is higher, maybe 446 degrees Fahrenheit. DOT 5.1 higher still. DOT5 silicone is way up there, like 500 degrees here.
But fluids don't stay fresh, do they? I hear brake fluid goes bad.
That's the critical thing to understand, especially with the common glycol-based ones. DOT 3, 4, 5.1, they're hygroscopic,
Hygroscopic, meaning?
meaning they absorb moisture right out of the air, even through microscopic pores in hoses and seals.
Water gets into the brake fluid?
Yep, over time it just happens. Now, a little water helps prevent pockets of pure water from causing rust, but there's a huge downside.
It lowers the boiling point.
Drastically. Even just 3–4% water contamination can drop the boiling point by over 100 degrees Fahrenheit.
Wow. So that 401 degrees Fahrenheit, 300 degrees Fahrenheit.
Easily. And 300 degrees arum is achievable during hard braking or long descents. Suddenly, that fluid you thought was fine boils, and you've got no brakes. That's why flushing old fluid is so vital.
And water causes corrosion too, right?
Big time. Especially if there are tiny bits of copper or brass wearing off internal parts. Water acts like an electrolyte. DOT5 silicone fluid doesn't absorb water, which sounds great. But it has other issues. It can trap pockets of water, doesn't mix with glycol fluids, can cause seals to swell if the system wasn't designed for it. So it's rare in standard cars.
So checking the fluid is important. Look for dark color.
Exactly. Fresh fluid is clear or light amber yellow. Dark brown or black means contamination, likely water, maybe other gunk. Time for a change.
Okay, so master cylinder makes pressure. Fluid's good.
Right.
Now it needs to get to the wheels, through the lines and hoses.
The veins and arteries of this system, absolutely. Brake lines are usually rigid, double-walled steel tubing, built tough to handle immense pressure, coated to resist rust.
And they have special ends, right? Flares.
Yep, precisely formed flares, double flares or iso-bubble flares, to create a perfect leak-proof seal when connected to fittings.
But they can't be rigid everywhere because the wheels move.
Exactly. That's where flexible brake hoses come in, usually made of reinforced rubber, sometimes braided stainless steel for performance applications. They connect the rigid lines on the car body to the moving parts, the calipers or wheel cylinders on the suspension.
Gotta handle all that bouncing and turning.
Constantly, which means routing is critical. You can't have them rubbing against things, kinking, or getting stretched too tight when the suspension moves. A worn or damaged hose is a major failure point.
So technicians check these really carefully.
Every inch. Looking for leaks, kinks, rust on the steel lines. On the hoses, they look for cracks, bulges, softening, any sign of wear. A bulging hose under pressure means it's about to burst. Very dangerous.
So it's not just a straight pipe from master cylinder to wheel. There are valves involved, fine-tuning things.
Oh yeah, several clever valves that manage the pressure distribution for better control and safety.
Like what?
Okay, first, you might have a metering valve. This is mostly on vehicles with front discs and rear drums. Its job is to slightly delay the pressure going to the front discs during light braking.
Delay the front. Why?
Because drum brakes often take a fraction longer to engage than discs. This valve lets the rear drums start working first, or at the same time, preventing the front brakes from doing all the work initially and potentially locking up too soon, especially for weight transfers forward. Helps keep things balanced, less nosedive on gentle stops.
Interesting. What else?
Then there's the crucial proportioning valve. This one manages front-to-rear brake balance, especially during heavy braking.
Heavy braking makes the car pitch forward, right? Takes weight off the rear wheels.
Exactly. Less weight on the rear means less traction. If you sent full brake pressure back there, the rear wheels would lock up instantly, causing a skid. Very dangerous.
So the proportioning valve reduces pressure to the rear.
Precisely. It reduces the pressure increase to the rear brakes, proportionally as overall brake pressure gets higher, prevents rear lockup, maintains stability. Some even sense vehicle load and adjust accordingly.
Smart. Okay, what other valves?
You have the pressure differential valve, often combined with the brake warning light switch on your dash.
The light that comes on if there's a problem?
That's the one. This valve sits between the two hydraulic circuits, front, rear, or diagonal. If there's a leak and pressure drops significantly in one circuit,
It senses the difference.
yes, a piston inside shifts off-center due to the pressure imbalance, and that movement physically closes a switch. Turning on your brake warning light, it's your immediate alert. Hey, something's wrong with the hydraulics.
Critical warning. Anything else?
Well, you have the stoplight switch. Simple, but vital. Activates your brake lights when you press the pedal. But in modern cars, it's often more than just a switch. It feeds information to the cruise control, ABS, ESC, sometimes even the engine computer. It's integrated.
Right, so it tells other systems the driver is braking.
Exactly. Fundamental signal for many safety and control systems.
You know, one thing you really notice in modern cars is how easy the brake pedal is to push, compared to, say, an old classic car without power brakes.
Oh, night and day difference, isn't it? That's power assist at work. Makes stopping effortless.
How does it do that? How does it multiply my force?
The most common system is the vacuum-operated booster. It's that big round thing usually mounted between the pedal linkage and the master cylinder.
Yeah, I know the one.
It cleverly uses engine vacuum. Inside, there's a large diaphragm. One side is exposed to engine vacuum. The other side can be opened to atmospheric pressure when you press the pedal.
So vacuum on one side, regular air pressure on the other.
Exactly. That pressure difference creates a strong force on the diaphragm, which then pushes on the master cylinder push rod along with your foot pressure. It dramatically multiplies your effort.
And it has a check valve, right, in case the engine stalls.
Crucial safety feature. A one-way check valve trapped vacuum inside the booster, so you still get one or two power-assisted stops even if the engine quits suddenly.
Good backup. What if a vehicle doesn't make much vacuum, like a diesel?
Good question. Diesels, some turbocharged engines or high-performance engines, often use a hydro boost system instead.
Hydro uses hydraulics, like power steering.
Exactly. It taps into the hydraulic pressure generated by the power steering pump to provide the brake assist. It's a very effective, compact system.
Does it have a backup too?
Yep, it usually has an accumulator, which is like a small pressure storage device. It holds enough hydraulic pressure for a couple of assisted stops if the engine or power steering pump fails.
Okay. And then there are electric and hybrid cars.
Right. They often use electronically controlled brake assist, ECBA. These are really sophisticated. They have to blend traditional hydraulic braking with regenerative braking.
Where the electric motor slows the car down and recharges the battery.
Precisely. The ECBA system manages that blend seamlessly, using electronic controls to decide how much regen and how much hydraulic braking to apply for smooth, efficient stopping and maximum energy recovery. They're very advanced.
Which leads us nicely into the really smart electronic systems. ABS, traction control, stability control. This is where the car actively helps prevent loss of control, right?
Absolutely. These are extensions of the core hydraulic system, but they use sensors, computers, and fast-acting valves to intervene in critical situations. It's all about enhancing safety and control beyond what the driver alone could manage.
So ABS, anti-lock brakes. What's its main job?
Simple purpose. Prevent wheel lockup during hard braking. If a wheel locks, it stops rotating and you lose steering control. You can't steer around the obstacle you're trying to avoid.
Right, skidding straight ahead.
Exactly. ABS prevents that. It uses wheel speed sensors, usually magnetic sensors reading teeth on a reluctor ring on the hub or axle.
Sensing how fast each wheel is turning.
Constantly. If the ADS control module sees one wheel suddenly decelerating much faster than the others, indicating it's about to lock up, it instantly commands the hydraulic modulator.
The modulator that has the valves.
Yep. Fast-acting solenoid valves. The module tells the valves for that specific wheel to rapidly release and reapply brake pressure, maybe 15, 20, even up to 60 times per second.
That's the pulsing feeling you get in the pedal.
That's it. The system is essentially pumping the brake for that wheel incredibly fast, keeping it right on the verge of locking but still rotating, so you maintain steering control while achieving maximum possible braking.
So key parts are sensors, the control module, the brain, and the hydraulic modulator, the valves and pump.
You got it. And bleeding these systems often needs a special scan tool to cycle those internal valves and pumps to get all the air out. It's not like the old days.
Okay, so building on ABS, what's traction control, TCS?
TCS uses the same wheel speed sensors as ABS, but its job is to prevent the drive wheels from spinning during acceleration.
Like on ice or gravel?
Perfect examples. If the system detects a drive wheel spinning significantly faster than the non-driven wheels, meaning it's lost traction, the control module steps in.
How does it stop the spinning?
It could do a couple of things. It might signal the engine computer to reduce power, maybe cut spark or fuel briefly, or close the throttle slightly. Or it can actually apply the brake lightly to just the spinning wheel using the ABS modulator.
Ah, so it breaks the wheel that's slipping.
Yep. That transfers torque to the wheel that does have traction on an open differential, or simply slows the spinning wheel down. Helps you accelerate smoothly without fishtailing.
Makes sense. And the ultimate system is ESC, Electronic Stability Control.
ESC is the big one. Mandatory on new cars in many places now. It's designed to prevent skids and loss of control during emergency maneuvers or on slippery surfaces, basically, keeping the car going where the driver is actually steering.
How does it know where I'm steering versus where the car is actually going?
That's the clever part. It uses the ABS wheel speed sensors, integrates TCS functions, but adds more sensors. A yaw rate sensor measures how fast the car is rotating or spinning.
Yeah.
A lateral acceleration sensor measures sideways g-force. And crucially, a steering wheel angle sensor.
So it knows the steering input and it knows how the car's actually responding.
Exactly. If it detects a mismatch, say, you're steering straight, but the yaw sensor shows the car is starting to skin sideways, oversteer, or you're turning the wheel but the car is pushing straight ahead, understeer.
It intervenes.
Instantly. The ESC module calculates which wheel or wheels need braking to correct the skid. It can apply the brake to just one single wheel, selectively, and reduce engine power.
So it might brake the outside front wheel to correct oversteer or the inside rear to correct understeer?
Precisely those kinds of subtle, individual wheel brake applications. It happens faster than any human could react, bringing the car back in line with your intended path. That flashing, skidding car light on your dash, that's ESC working.
Incredible technology, but complex. So how do technicians diagnose problems in these systems? It's not just looking for leaks anymore.
Not at all. It's heavily reliant on electronics now. Technicians use sophisticated scan tools way beyond basic code readers. These tools talk directly to the ABCC control module.
What can they see?
They retrieve diagnostic trouble codes, DTCs, which point to specific faults like yaw rate sensor circuit malfunction. But more importantly, they show live data.
Real-time sensor readings.
Exactly. They can see the speed reported by each wheel sensor, the steering angle, the yaw rate, the G sensor reading, brake pressure sensor readings, everything the module sees.
So if one wheel sensor reads 0 while driving,
Bingo. You know exactly where to start looking. Sensor, wiring, tone ring. It allows for incredibly precise diagnosis. It's like digital detective work. Technicians also rely heavily on technical service bulletins, TSBs, from the manufacturers. These highlight known issues or updated repair procedures. Because these systems are so interconnected, a problem in one area can trigger codes in another. You need the right info and a systematic approach. The systems just are complex, and fixing them requires objective data.
okay, let's shift gears slightly, back to the more mechanical side. Drum brakes, you said they're still common on rears. How do they actually work?
Drum brakes are a classic design, pretty robust. You have a stationary backing plate bolted to the axle housing or knuckle. Mounted on this plate are two curved brake shoes.
With friction material on the outside.
Exactly. These shoes sit inside a heavy cast iron drum that rotates with the wheel. When you hit the brakes, hydraulic pressure goes to a wheel cylinder mounted on the backing plate, usually at the top.
And that pushes the shoes outward?
Right. Pistons inside the wheel cylinder push the tops of the shoes out, forcing the friction lining against the inside surface of the spinning drum. Friction slows the drum, and thus the wheel.
What holds the shoes in place? Springs.
Lots of springs. Strong return springs pull the shoes back away from the drum when you release the pedal. Hold down springs keep the shoes flat against the backing plate. There's usually an anchor pin that the shoes pivot against. And, very importantly, an adjuster mechanism.
To account for wear.
Yep. As the linings wear down, the shoes have to travel further to contact the drum. The adjuster keeps the shoes close to the drum automatically.
And you mentioned a duo servo design. What's that?
Ah, yeah, that's a common and clever design. It's self-energizing. When the leading shoe, the one facing the direction of drum rotation, contacts the drum, the friction actually wedges it tighter against the drum.
So the drum's rotation helps apply the brake.
Exactly. And then, through an adjusting link, that leading shoe pushes the trailing secondary shoe even harder against the drum. It creates this sort of chain reaction, significantly boosting the braking force without needing as much hydraulic pressure. It makes them quite powerful.
And the self-adjusting mechanism, how does that work?
Usually involves a star wheel adjuster. Often there's a cable or lever linked to the parking brake mechanism or activated when braking in reverse. Each time it activates, if there's enough clearance, meaning the linings have worn, it clicks the star wheel one notch, expanding the shoes slightly to maintain that ideal close but not touching clearance. Keeps pedal travel consistent.
So what typically goes wrong with drum brakes? What are technicians looking for?
Drums themselves can develop problems. Scoring deep grooves, bell mouthing worn wider at the opening, out of round or uneven wear causing pulsation, hard spots from overheating which cause grabbing or noise, heat checks little cracks from too much heat.
And these affect braking feel.
Absolutely. Pulsation, noise, pulling to one side, reduce stopping power, and drums have a maximum diameter. If they're machined beyond that to clean them up, they're too thin, can't handle heat, got to be replaced.
What about the shoes and other parts?
Shoes need checking for lining thickness, obviously, but also for cracks or contamination from leaking wheel cylinders or axle seals, oil or grease on the linings. Forget about stopping power.
Ruins them.
Instantly. And it's always best practice to replace all the hardware, the springs, hold-downs, adjusters, whenever you do the shoes. Springs lose tension over time, affecting performance and return.
Wheel cylinders leak.
That's a common failure. Check for wetness around the rubber dust boots. Any leak means it needs rebuilding or, more commonly, replacement. And then careful bleeding afterwards.
And adjustment is key, you said.
Critical.
Right.
If they're too loose, you get a low pedal, long travel before they bite. Too tight, and they drag constantly, overheat, wear out fast. Gotta get that adjustment just right.
Okay, let's talk discs. They're pretty much standard now, especially on the front. What makes them so much better, generally?
The biggest advantage is heat dissipation. Drums trap heat inside. Discs are open to the air, often vented with internal fins, so they cool much, much more effectively.
Less prone to brake fade on long hills or hard use?
Way less prone.
Mm.
Fade happens when things get so hot the friction material doesn't work as well or the fluid boils. Discs manage heat better. The system is also simpler conceptually. You've got the rotor The disc itself bolted to the hub.
Spinning with the wheel.
Right. And then the caliper assembly that fits over the edge of the rotor, like a clamp. Inside the caliper are the brake pads, one on each side of the rotor, and one or more hydraulic pistons.
So pressure pushes the piston, piston pushes the pad into the rotor.
Exactly. Piston pushes the inboard pad. Depending on the caliper type, it either pushes pistons on the other side too, or the whole caliper slides and pulls the outboard pad in. Either way, it clamps the pads onto the rotor surfaces, creating friction.
You mentioned caliper types, fixed versus floating.
Yeah, two main types. Fixed calipers don't move. They're rigidly mounted. They have pistons on both sides of the rotor pushing inwards. Often found on performance cars, heavy trucks, more clamping force, better feel sometimes.
Okay, and the other type?
Sliding or floating calipers. Much more common on everyday cars. These usually have pistons on only one side, the inboard side. When the piston pushes the inner pad, the entire caliper body slides on guide pins or bolts.
Pulling the outer pad against the rotor.
You got it. It clamps by sliding. Simpler design, fewer parts, generally cheaper to make, works very well. That's what most cars have.
Disc brakes are pretty robust, but they still have issues. What are the common complaints or things to look for?
Noise is a big one. High-pitched squeal, often worn pads, missing anti-rattle clips, or sometimes just the pad material itself. Chatter or groan could be caliper issues, sticking slide pins, maybe a piston not retracting properly. A rumble might be a severely warped rotor, or even a wheel bearing issue.
And pulsation, that shaking pedal, usually the rotor.
Almost always the rotor. Two main causes. Lateral runout, which is side-to-side wobble. Measured with a dial indicator, it needs to be tiny, like a few thousandths of an inch. Too much wobble pushes the pads back and forth, causing pulsation.
And the other cause?
Thickness variation, also called parallelism error, means the rotor isn't the same thickness all the way around. As the thicker and thinner spots pass through the pads, it causes that pulsation.
How do you check for that?
With a micrometer, measuring thickness at multiple points around the rotor needs to be extremely consistent. Rotors also have a minimum thickness spec stamped on them. Wear or machine them below that, they must be replaced. Too thin, they warp easily, can't handle heat, could even crack.
And visually, scoring cracks.
Yep, look for deep scores, obvious heat cracks, or blue glazed hard spots from excessive heat. All signs the rotor needs attention, either machining, if possible, or replacement.
What about the caliper itself? Did they get rebuilt?
Sometimes. If a caliper is leaking fluid from the piston seal, or the piston is stuck, seized, and won't move freely, or the bore is badly corroded, an overhaul might be needed.
Which involves?
Taking it apart, carefully removing the piston, inspecting the bore, replacing the rubber seals, piston seal, dust boot, cleaning everything meticulously and reassembling, restores proper function.
And pads. Just check thickness.
Thickness is key, but also check for even wear, any signs of contamination, oil grease, and make sure they fit correctly in the caliper bracket. And crucially, when installing new pads, they need to be burnished or bedded in.
Bedding in. What's that?
It's a specific procedure of moderate stops after installation. It transfers a thin, even layer of pad material onto the rotor surface, creates a matched set, ensures best performance, quiet operation, and proper friction characteristics right from the start. Very important step.
Okay, one more system. The parking brake. Even when parked, something's holding the car, right?
Yep, the parking brake or emergency brake. Critically, it's usually a purely mechanical system, totally separate from the hydraulics. That's its backup function. If hydraulics fail, you still have this.
Operated by cables.
Usually. Cables run from a hand lever or foot pedal inside the car back to the rear brakes typically.
How does it apply the brakes at the wheels?
Depends on the rear brake type. If you have rear drum brakes, the cable mechanism usually just levers the existing drum shoes directly against the drum. Simple and effective.
What if you have rear discs?
Two common ways. Many cars with rear discs actually have a small, separate drum brake built inside the center hat section of the rear rotor. The parking brake cable activates those little shoes.
Ah, drum and hat system.
Exactly. Or the parking brake mechanism can be integrated directly into the rear disc caliper itself. Often uses a screw or cam mechanism inside the caliper piston to mechanically push the main disc pads against the rotor when the cable is pulled.
And now we're seeing electronic ones too?
Increasingly common. Electronic parking brakes, EPBs. They replace the cables and levers with small electric motors at the calipers activated by a button. Often have features like auto hold on hills or automatic application release. Cleaner interior design too.
So what maintenance do parking brakes need? Adjustment seems key.
Adjustment is absolutely crucial. But first, inspection. Check the cables for any fraying, rust, kinks, or signs of binding. A sticky cable can cause the brake to drag or not hold properly. Check the lever or pedal operation should feel smooth.
And the adjustment. Too tight or too loose is bad.
Both are bad. It needs to be adjusted tight enough to hold the vehicle securely on a reasonable incline without needing excessive lever pedal travel. But it must release completely when off with zero drag. Too tight causes drag, heat, wear. Too loose, and well, your car might roll away. Gotta find that sweet spot.
Okay, last component area, but definitely not least, wheel bearings. Tucked away, but sounds like they're vital.
Absolutely fundamental. They do several jobs. They support the vehicle's weight at each wheel, obviously. They allow the wheel to rotate freely with minimal friction. And they have to handle huge forces, sideways forces, during cornering, braking forces, impacts from bumps.
Without them, the wheel wouldn't spin right or stay attached.
Pretty much. And if a bearing is bad, it can affect braking because the rotor or drum won't be spinning true.
Are there different kinds?
Yes. Older designs often use tapered roller bearings. These are separate inner and outer bearings with tapered rollers. They're adjustable and need periodic cleaning, greasing, and careful adjustment for end play. A tiny bit of allowed movement.
Tricky to adjust right.
Requires precision. Too tight, they overheat. Too loose, they wear out fast and the wheel wobbles.
What's more common now?
Sealed units. You might have a non-integral design where the sealed bearing cartridge is pressed into the steering knuckle or hub carrier, or, very common now, the integral hub and bearing assembly.
The whole hub and bearing is one piece.
Yep. Sealed for life, pre-adjusted. Often includes the wheel studs and the ABS sensor ring reluctor. If the bearing fails, you replace the entire assembly. Easiest to replace, but usually the most expensive part.
How do you know if a wheel bearing is going bad? What are the signs?
The classic sign is noise. A humming, rumbling, or growling noise that changes with speed and often changes pitch or intensity when you turn.
Like it gets louder turning left if the right bearing is bad.
Exactly, because turning loads the outside bearing. Another check is for excessive wheel play. Jack the wheel up, grab it top and bottom, 12 and 6 o'clock, and try to wiggle it. Any significant looseness or clunking points to a bad bearing.
Can affect tire wear too.
Definitely. A wobbly wheel won't run true, can cause cupping or uneven wear on the tire tread. In really bad cases, you might feel vibration or even notice excessive heat at the hub after driving.
And replacing them. Torque is critical, right?
Absolutely critical, especially for the hub nut on integral assemblies or the spindle nut on tapered bearings. Manufacturers' torque specifications must be followed precisely. Incorrect torque can destroy a new bearing very quickly or lead to dangerous looseness. Same goes for wheel, lug nuts. Always torque them properly in the right sequence. It's all about safety and longevity.
Okay, wow. We've covered a lot of ground, from basic physics to complex electronics. So, wrapping this up, what does all this mean for us, the drivers?
I think the biggest takeaway is just how much sophisticated engineering goes into that seemingly simple act of stopping. It's this incredible interconnected system.
Not just one thing, but hydraulics, mechanics, electronics, all working together.
Precisely. And every part, from the fluid itself to the bearing supporting the wheel, plays a vital role in your safety. It's a system built on redundancy and precision.
So for you, our listener, hopefully this deep dive gives you a real appreciation for the tech in your car. Next time you brake, you'll know it's this symphony of forces.
Yet, a symphony of Pascal's law, friction, sensors, and algorithms. And maybe you'll have a better feel for the complexity involved if you ever need service. Understanding the knowledge needed, especially for ASE-certified techs, highlights the value of real expertise.
Definitely. So here's a final thought to chew on. We're seeing more and more advanced driver assistance systems, ADS. Things like automatic emergency braking, adaptive cruise that brakes for you. How is this changing our actual relationship with driving? Are we becoming passengers in some ways?
That's a great question. And tied to that, what does it mean for the technicians of the future? Will they need to be more like software engineers diagnosing code than mechanics turning wrenches? Or will that hands-on skill always be fundamental, just augmented by digital tools? Lots to think about.
Definitely something to mull over.
Yeah.
Thanks for joining us on this deep dive into the world of brakes.